Good afternoon. My name is Jason Wong, and this is my lab report for Lab 5 for Physics 2211. In this lab, we had the opportunity to choose our own adventure and analyze a video with Tracker and create a relevant computer model with GlowScript and VPython. For my lab, I will be observing the trajectory of a ping pong ball when thrown at a cup from across the table. First, I will use a video of me shooting the ball towards the cup and gather positional data for the Tracker analysis. Next, I will use GlowScript and VPython to model the motion, and then I will compare the data from Tracker to the modeled motion to evaluate my code, and finally we will discuss the results of the model and next steps. This lab is similar to Lab 2, where we took a look at the falling object from rest. The difference is that this time there are initial velocities in both the x and y directions. The formulas that we will be using in this lab are the force of gravity and drag that make up the net force and Newton's second law to update the positions and velocities throughout the clip. You will notice that the drag formula is not the same as the one that we used in Lab 2. I used the full drag force formula and used the values provided by Allain from Southeastern Louisiana University for the drag force of the ping pong ball. Here's the clip that we will be analyzing in Tracker. The coordinate plane is set at the edge of the table that I'm standing at. The calibration stick is set for the length of the table, which is 6 feet or 1.8288 meters. We can see here that the y-axis isn't parallel with the edge of the trophy case. This could indicate issues with the perspective and orientation of the camera angle. I will mention this later in our assumptions. First, we needed to build the scene in VPython to visualize what was going on in the clip. This included the table, the cup, and the trajectory of the ball and the ball itself. Next, we set up the system properties. The mass of the average ping pong ball is 0.0027 grams. The initial position is taken from the Tracker data, and the initial velocity is calculated by finding the average velocity between the second and first data point. I experimented with using different data points and found that the first and second points resulted in the most accurate data. The values to use for the drag force are from Allain's article as follows. The drag coefficient is set for 0.47, which is typical for a spherical object. The cross-sectional area of the object is set as pi times the radius of the ball squared, and the density of the air is typically 1.2 kilograms per meter cubed. Now, we will set up the for loop with the forces that we mentioned earlier. One thing to note on this slide is that even though time is set to 2 seconds, the model will stop simulating as soon as the ball breaks the top plane of the cup. Here, we can see the predicted trajectory of the ball in VPython. With both drag and gravity forces accounted for, we can see that the simulated throw also makes the ball into the cup. Now we can see all the data gathered from Tracker graphed with the simulated data with both gravity and drag. When gravity and drag are both considered, both graphs show that the model with both gravity and drag follows the Tracker data almost exactly. As for all experiments we conduct, there are always assumptions that you need to make to perform them. Human error in Tracker, which can be embodied in the labeling of the point mass positions, the setting of the coordinate plane, and the calibration stick, are always present, and needs to be considered when discussing assumptions for the experiment. The initial velocity was calculated as the average velocity between the first two data points. This doesn't mean that it was the exact initial velocity of the ball leaving my hand, but it was a good enough estimate to model the motion. We also need to consider that there can be discrepancies in the drag force calculations. One example is that the altitude can have effects on the air density value. Like I mentioned earlier, the camera angle can also create errors in the data generated from Tracker. And finally, there can be measurement errors in real life. I used a tape measure to measure the table and the cup, but these values can be a little bit off when putting them into code. Playing pong and shooting pong balls into a cup are very similar to playing basketball. There's this concept of arc that can give you higher or lower margin of error of making the goal. As we see here, a perpendicular 90-degree shot has the most diameter of the target, but as the angle of approach decreases, the margin of error also decreases, requiring a more accurate shot. From the graphic, we can see that the optimal shooting arc is at 45 degrees. However, we need to consider the distance away from the target and the initial velocity that ball should leave your hand. With all that, I plan to analyze some of the throws of some of my other fraternity brothers and look at release points and initial velocities. I can then combine physics principles with a little bit of probability to extrapolate the quote-unquote ideal pong throw. A group called Empire Robotics has created a robot that can throw a perfect shot into a cup. I would like to look more into this and see if I can build a robot that throws similarly. Thank you for a great semester. I really enjoyed making this lab from start to finish.